Dr. Eddy is ISEC's Board of Directors Secretary and the study lead and editor of the 2021 study entitled Space Elevators and the Green Road to Space. Over his 42 years of teaching, he was a professor of physics at Indiana University at Pennsylvania and Science Department, chair at the Stony Brook School in New York. So it's our pleasure to welcome Dr. Jerry Eddy.
Thank you very much. I'll try to share my screen. Okay. So ISEC has just completed this 18-month study, the Green Road to Space, and it should be, what's showing on your screen is the cover page of the report and the fact that it is now available on our website, and you can download it and peruse it at your convenience. You'll see there's a significant list of authors. There are several chapters that have been written by different people. As you've heard, David, Dr. Dotson has written chapter 3 and presented it to you already. It was supposed to follow mine in the first place. Okay, so the main purpose of the study was to see if and in what ways the space elevator could environmentally benefit the Earth. I will outline what we found, show some detail of the major findings. The study assumed a complete operational space elevator system, which is called galactic harbors, except that we also considered, to a certain extent, the environmental impact of the construction and the operation of the galactic harbor, in which we found it to be near zero environmental impact. We then focused on what benefits the space elevator could have on the Earth itself. Three major things that were considered were not new ideas, but ones that were dreamed of in the early days of the space program. These, of course, were space solar power, which David presented, nuclear waste disposal, and Earth-Sun shades at L1. In each of these, we contrasted the use of the space elevator to that of using rocket launches to accomplish the same end result. The author of the space solar, well, I was about to introduce David, which of course we already have done. I will cover the other two ideas and touch on a few additional ones that were considered. Bert Malloy did the main research and wrote most of the chapter on high-level nuclear waste. The idea of sending nuclear waste off into space is not new and was basically shelved because of the consequences of a possible rocket failure with nuclear waste on board. The space elevator eliminates that possibility. Bert researched all types of nuclear waste, but focused on spent reactor fuel and nuclear weapons because of the extremely long half-lives there that are involved. His research looked at all the various current ways it is contained and stored. The main result of this study found that it is a monumental problem and has minimal success for safe and long-term storage. So how much nuclear waste are we actually talking about?
Hey, Jerry, your slides are not moving forward.
There we go. Okay.
Nope, still got the original one.
Oh, God.
There you go.
All right. I don't know what I did to make it happen, but okay.
Uh-oh.
Well, we'll find out on the next one. We're not interested in the details of this chart yet. I'll be explaining those later, but the total that I'm interested in here is the fact that it's 810,000 tons. Naturally, we want to dispose of the high-level waste in such a way that it is no longer poses a threat to Earth and our way of life. Currently, the consensus among nuclear nations is deep geological repositories. There are several interesting driving functions that are at play regarding this approach. Some of this waste has to be stored for up to 500,000 years. Therefore, disposal implies it must be extraordinarily unlikely for humans to encounter it accidentally or purposefully, and that no natural or geological processes will make such exposure possible. The U.S. to date is the only nation to have actually done a significant amount of construction on such a site, Yucca Mountain in Nevada. However, the many delays since the project started have made the future of the Yucca Mountain facility extremely uncertain at best. Finland started planning for a similar project in 1983 and plans to finally apply for a license this year, with hopes to begin actual depository operations in 2025. Yes, 42 years later, actual usage may occur. Sweden had a similar problem, and their project is presently on hold. France chose a site in 1999. Construction was expected to begin in 2022, with initial waste disposal by perhaps 2030. But opposition to the project appears to be intensifying. Russia may also be getting a bit closer, since it has selected a site. Opening is not planned to occur till 2030. So, how is it presently stored? This slide shows one example which has been recently developed and is now widespread. It is a method of chemically immobilizing the waste, which involves heating the waste with glass-forming materials to an extremely high temperature until liquid glass is formed. This is then poured into steel containers, forming a material like ceramic, and then permanently sealed called vitrified. These containers contain about 9.5 tons and can easily be carried by a space elevator, which can handle loads up to 14 tons, as we've already seen. One of the main problems is that spent nuclear fuel bundles can no longer safely remain in the reactor and be of significant economic benefit, have to be removed and stored under several meters of circulating water in an extremely large pool. Construction from reinforced metal-lined concrete. The pool is usually adjacent to the reactor building. This is commonly known as wet storage. Later, the spent nuclear fuel rods is either sent to a reprocessing laboratory or goes to a repackaging facility, and then to dry storage. Reprocessing the spent nuclear fuel leads to newly usable fuel. Reprocessing also leads to high-level waste products of only about 1/5 the original volume, but still dangerously reactive for several hundreds of millennia. Table also shows estimates based on the planned expansion by several nations for periods from 2019 through 2030 and 2031 through 2050. So the total already accumulated from weapons is shown additional here, vitrified, repackaged, and wet, along with the two future estimates, giving the total of 810,000 tons that we mentioned before. To take West to space on the space elevator would mean that it would be limited to the carrying capacity of the tether climber, initially 14 tons a day. Since some of the storage containers are heavier, they would have to be repackaged into smaller containers. It is likely that because of the climber's limitation, high-level nuclear waste containers in the future would be redesigned to allow direct shipment to the galactic harbors. Looking at the throughput, we see that the mature set of 3 galactic harbors in each of the 2 tethers, a total amount of cargo that could be carried would be 84 metric tons per day and 30,660 tons per year from about 240 to 247. The chart shows that a projected throughput in the future when additional elevators are added would increase that amount greatly. So what happens after it arrives at apex anchor? We see that in this diagram, you see the Earth, you see the elevator out to 100,000 kilometer altitude. When the elevator is in position toward the sun, the load would be released. And we see that the apex anchor velocity is such that the difference allows a velocity of 21.94 kilometers per second, which would put the package into an orbit around the sun, but could still reach the sun when it got to perihelion. So when the craft reaches aphelion, an attached rocket would be fired to give it a new orbit well within the Earth's and never to have to be dealt with again. Having a safe, permanent storage way of dealing with high-level nuclear waste would encourage a greater use of nuclear power to meet the future electrical needs of our planet, and doing it in a non-polluting manner. The second benefit that I want to talk about was proposed by Dr. Roger Angel, a professor at Arizona University in 2006. He proposed the idea at a National Academy of Science conference in May and received a grant from NASA just a few months later in October. He proposed to put a sunshade in space at the L1 position between the Earth and the Sun. It is where the object with the correct orbital velocity would stay permanently in orbit directly between the Earth and the Sun. The plan is to make trillions of 2-foot in diameter discs, ultra thin, about a gram each. As shown in the diagram, the distribution of the flyers is designed to spread out in an area. This is how Dr. Angel described it. The plan would be to launch a constellation of trillions of small, free-flying spacecraft 1 million miles above Earth in an orbit aligned with the Sun, called the L1 orbit. The spacecraft would form a long, cylindrical cloud with a diameter about half that of the Earth and about 10 times longer. About 10% of the sunlight passing through the 60,000-mile length of the cloud, pointing lengthwise between the Earth and the Sun, would be diverted away from our planet. The effect would be enough to uniformly reduce sunlight about 2% over the entire planet, balancing the heating of a doubling of atmospheric carbon dioxide in the Earth's atmosphere. Researchers have proposed various alternatives for cooling the planet, including aerosol scatterers in the Earth's atmosphere. The idea for a space shade in L1 to direct sunlight from Earth was first proposed by James Early at the Lawrence Livermore National Laboratory in 1989. The earlier ideas were for bigger, heavier structures that would have needed to be manufactured and launched from the moon. Angel said, "I wanted to make the sunshade from small flyers, small, light, and extremely thin spacecraft that could be completely assembled and launched from Earth in the stacks of 1 million at a time. When they reach L1, they would be dealt off the stack like cards into a cloud. So there would be nothing to assemble in space. The lightweight flyers designed by Angel would be made of a transparent material 1 meter in diameter, pierced with small holes. Each would be 1/5,000th of an inch thick and weigh about a gram, the same as a large butterfly. It would use MEMS technology mirrors as tiny sails that tilt to hold the flyers in position in the orbiting constellation. The flyer's transparency and steering mechanism prevent it from being blown away by radiation pressure from the sun. The total mass of all the flyers making up the space sunshade structure would be 20 million tons. At $10,000 a pound, conventional chemical rocket launches is prohibitively expensive. Angel proposes using a cheaper way, developed by Sandia National Laboratories for electromagnetic space launches, essentially a railgun, which could bring costs down to as little as $20 a pound. Once propelled beyond the Earth's atmosphere and gravity with electromagnetic launchers, the flyer stacks would be steered to L1 orbit by solar-powered ion propulsion, a new method proven in space by the European Space Agency Smart 1 Moon Orbiter or NASA's Deep Space One probe. The concept builds on existing technologies, Angel said. It seems feasible that it could be developed and deployed in about 25 years at a cost of a few $1 trillion. With care, the sunshade could last about 50 years. So the average cost is about $100 billion a year, or about 2/5 or 2/10 of 1% of the global domestic product. He added, the sunshade is no substitute for developing renewable energy. which is the only permanent solution. A similar massive level of technological innovation and financial investment could ensure that. But if the planet gets into an abrupt climate crisis that can only be fixed by cooling, it would be good to be ready with some shading solutions. The idea was to do this only in a global emergency. So how could this be done? Well, it's in a very similar manner to the nuclear waste. You see the same initial velocity given to the flyers, but then when they reach near the sun, the first burn will occur, putting them in a orbit inside Earth. Then a second burn would be necessary to make that orbit more circular and actually then be adjusted to reach L1 position. The total mass needed is about 20 million tons. Again, an enormous amount of rocket launches would be needed to handle it, as Dr. Angel realized. Thus, the Saturn V rocket would take 1,200 years, certainly longer than our modern rockets, but they which would still be quite a long time. With the space elevator at initial operational capacity, it would take about 652 years, again, a very long time. When the elevator reaches robust performance, however, we see that it could be done in 11.5 years, a much more reasonable time. But if the planet gets into an abrupt crisis that can only be fixed by cooling, it would be a good idea to be ready with some shading solution that has been worked out. The space elevator could do it in a crisis and make cheaper and greener than any other means. I have a few other ideas to give you some thought on. First of all, polluting industries on the Earth could be set up at GEO. Thus, raw materials could be sent up on the climbers and finished products returned to the Earth. Since refining happens to be the most polluting industry, it would be obvious to refine materials collected from mining asteroids at GEO before sending them back to the Earth. And of course, these refining industries could be set up using the space elevator. Industries making heavy devices for space, particularly, could be done at GEO. Materials sent up on the elevator, then assembled in the weightless environment of space. So my time is about up. I'd just like to point out that there are a couple more chapters in the report that continue with this theme, that the space elevator is the green way to space. I'll be happy to answer any other questions that you might have.
Dr. Jerry Eddy, does anybody have any questions for him?
Since there is a few minutes left, I might point out one of my other slides here that you might find interesting. This shows the 12 items that the Environmental Protection Agency considers in giving a during an environmental impact study. Very few of these pertain to the space elevator. The very few that do would be in terms of the operation of the spaceport or Earthport, and those are almost the same as any oil platform. Thus, we can claim or do claim that the space elevator in operation would be near zero impact. Thank you very much.
Awesome. Thank you so much, Dr. Eddy. I know that the geoengineering is a very interesting topic. You have a couple more minutes. Do you want to elaborate a little bit more on anything?
Let's see, there's one other item, I think, maybe if I can back up one slide. No, I guess not, unless there's questions.
All right. Any questions?
Can I make a little addition here? I think the report that Jerry is editing and the other authors are contributing chapters to is a monumental movement forward, recognizing that there's a difference between rockets and space elevators. We believe that it's a dual space access architecture that we need to go forward with, and we need both, but we have to make sure we understand the impacts of both. And the real thing that people don't comprehend, at least I'm projecting they don't comprehend, is that if you have train tracks to space, you can do missions you have never planned on doing before. You might have talked about them, but you never planned on it. And I use the example, the L5 colony. You know, Dr. O'Neill and Jerry actually met Dr. O'Neill way back, and we talk about that. It turns out that Dr. O'Neill came up with this concept and had his students designing this colony in space back in the 60s and 70s. And we've talked about it. And the only answer that anybody came up with is, let's go form a corporation on the moon and develop it on the moon and ship it to L5. Except that implies you put a colony on the moon that has to do oxygen and water and structures and everything for someplace else. And so, wait a minute, they got to develop their own colony on the moon first. Then you can do your colony out at L5. Because the answer is you could not lift off 11 million tons to L5. So the point Jerry's making is we can do environmental lifts and take stuff to L5 and not impact the Earth. And we can enable missions that you can't do with rockets, really. So that, I mean, everybody's admitted you can't do L5 colony with rockets. So it's kind of intriguing. And I think this report is going to stand up by itself and say space elevators are a good choice. And the only question is, can we build it? Now, the space elevator guys say we can. So we have to prove it. It's on our shoulders to prove that we can put up this environmentally green transportation permitted infrastructure for space. So thanks, Jerry, for doing that and leading the activities.
I'd just like to add one thing. And Peter mentioned that I met Dr. O'Neill. I actually was at a conference on small accelerators, which was my specialty. And he was the keynote speaker. And one of the interesting things is that the purpose of the L5 colony was to build and place solar collectors.
Right. So you had to build a colony at L5 before you could do SPS.
Basically, yes.
Yeah, interesting. But of course, you can't do the colony at L5 until you do the colony on the moon.
Yeah.
So taking space elevators, putting them in that equation circumvents so many problems. So we need people to think about space elevators enable missions. They're not just cheaper, they enable the missions. It can't be done otherwise. Okay, exactly. Thank you, Jerry. That was great.
Thank you.
All right, awesome. Thank you so much, Dr. Eddie, for that.